Welcome to this explainer. Today, we're popping the hood on AI and data mining. We hear so much about these flashy algorithms, predictive models, and cutting-edge AI. But we're going to discover a much less glamorous truth. Those brilliant algorithms, well, they're really only as good as the messy, unwashed data they're fed. Literally, if you put garbage in, you're going to get garbage out.
Okay, let's dive right in with a quick reality check. This is a quote from data warehousing pioneer Ralph Kimball, who famously noted that data cleaning is one of the 3 biggest problems in data warehousing. Actually, a DCI survey even called it the #1 problem. And why is that? Because without quality data, you get absolutely no quality mining results. If your data is full of duplicates or just missing fields entirely, you end up with incorrect, highly misleading statistics. Quality decisions absolutely require quality data. So this explainer is going to serve as your systematic roadmap through the 5 major tasks of pre-processing. We'll look at the dirty data problem, data cleaning, data integration, data transformation, and finally, data reduction. We are taking you from raw, dirty ingredients all the way to a sleek, manageable data warehouse.
Let's start with section 1, the dirty data problem. Because the unavoidable reality here is that real-world data is just, well, dirty. So the crucial point we really have to establish right off the bat is that real-world data is fundamentally flawed. It acts as a massive roadblock to accurate statistics. But how does it get so dirty in the first place? Well, it generally falls into 3 buckets. First, it's incomplete. This means it's lacking attributes, like, say, an unrecorded occupation. This is often just due to human error, some misunderstanding at data entry, or even hardware problems. Second, it's noisy. This means it contains weird errors or wild outliers. Imagine seeing a salary listed as -$10. That usually results from faulty collection instruments or transmission errors. And third, it's inconsistent. This happens when you have discrepancies in codes or names across different sources.
And what we're looking at here brilliantly illustrates just how frustrating data inconsistency is out in the wild. Imagine you're a data analyst trying to merge 2 sales databases. System A uses the label customer_ID and rates customer satisfaction on a scale of 1, 2, and 3. But meanwhile, System B uses cust number and rates satisfaction using A, B, and C. Or maybe someone's age is listed as 42, but their birthday is recorded as March 7th, 1997. The math simply doesn't add up. And algorithms, they literally cannot process this without human intervention.
Let's move on to our actual solutions. I want you to think of this whole pre-processing operation as a literal car wash that scrubs down our database before we can actually use it. We take our dirty-looking data, run it through the soap and water of cleaning, integrate the different pieces, transform the numbers, and reduce the overall volume. What we get out the other side is a shiny, clean-looking dataset perfectly ready for mining.
That brings us right to section 2, data cleaning. This is where our main focus is fixing that dirty data, with the primary goals of filling in missing values, identifying those weird outliers, and smoothing out the noise.
It's such a common headache. Just picture a massive sales database where thousands of rows, or tuples as we call them, have absolutely no recorded value for the customer's income. Maybe the equipment malfunctioned, or, maybe the customer just flat out refused to enter it. So how do we actually handle these massive gaps without just deleting everything and losing all that valuable information?
Well, we have a few options. We could just ignore the tuple entirely. This is sometimes done for classification tasks, but it's really not effective if the percentage of missing values is high. We could try filling in the values manually, but come on. For a massive data warehouse, that is way too tedious and practically infeasible. Instead, we can automate it. We can use a global constant, like filling every blink with the word unknown. Or we could do a smart fill, using the attribute mean, so the average, for all samples belonging to that same class. And finally, we can even use statistical models to fill it with the most probable value.
Now, what's really interesting is how we handle the noisy data, those random errors and wild variants. We can actually mathematically smooth out this variance using a super simple 4-step recipe called the binning method. First, you sort your raw data points in ascending order. Second, you figure out the number of bins or buckets you need based on the maximum and minimum values. Third, you group the numbers into these bins and calculate the mean average for each specific bin. And finally, you smooth the data by replacing all the original varying numbers in that bin with that mean average. It completely flattens the noise and gives the algorithm a clean, readable trend.
Once our data is washed and smoothed, we move to section 3, data integration.
This step is all about combining data sources, taking multiple diverse databases, data cubes, or files, and merging them into one cohesive source. But as you can probably guess, combining databases introduces a massive headache known as the entity identification problem. And it's exactly what it sounds like. Our systems have to figure out if differently named records are actually the exact same person or object. As we saw earlier, how can the computer be absolutely sure that customer ID in database 1 is the exact same metric as cus number in database 2? Resolving this is absolutely critical to avoid duplicating records.
During this integration phase, we also have to hunt down redundancies, specifically what we call derivable data. We've got to make sure we aren't wasting precious storage space. For example, if we already have a customer's date of birth and the current date in our system, we definitely don't need a separate column storing their age. Age is a derivable attribute. The same goes for annual revenue if we already have their monthly sales figures. We detect these overlaps using correlation analysis, and then we just eliminate the redundancy.
Okay, so our data is clean and successfully integrated. Let's dive right into Section 4, Data Transformation. This is where we focus on normalizing the data to make them math manageable for our algorithms. In transformation, we scale data so it falls within a small specified range. Think about it this way. If an algorithm is trying to compare a customer's age, which is usually somewhere between 18 and 100, with their income, which might be anywhere from $12,000 to $98,000, those massive numeric differences are going to totally skew the math. But through techniques like min-max normalization, we can scale that income down to a simple decimal between 0.0 and 1.0. So an income of $73,000 might just become 0.716. We can also use z-score normalization, which uses the mean and standard deviation, or decimal scaling, which simply moves the decimal point. Basically, it puts all our data on an even playing field.
Finally, we reach Section 5, Data Reduction. Our goal here is shrinking data volume, which is vital because a modern database might literally store terabytes of data. Running complex analysis on a completely unreduced dataset would take a practically infinite amount of time. So our goal here is to get a reduced representation of the dataset that is way smaller in volume but produces the exact same, or at least almost the exact same, analytical results. One way we pull this off is through data cube aggregation. Instead of feeding the algorithm hundreds of granular daily sales records, we gather and express the information in a summary form. For instance, we can compress 4 highly detailed quarters of sales data from 2018 and 2019 into a simple single yearly sales summary. We drastically reduce the volume, but the analytical insight, it remains entirely intact.
And what we're looking at here brilliantly illustrates another strategy called attribute subset selection. The idea is to completely drop irrelevant or weakly relevant attributes to shrink the overall data size. By using a decision tree, the system tests different attributes. Say we start with attributes A1 through A6. The tree might help us realize that to classify our data accurately, we actually only need A1, A4, and A6. The probability distribution remains super close to the original, but our data volume is slashed right in half.
We can further shrink our data footprint using a few other clever strategies. With dimensionality reduction, we might eliminate things like stop words entirely in feature extraction just to save space. With numerosity reduction, instead of keeping a list of every single overlapping number, we can replace them with a histogram or use the mathematical midpoints of a range. And lastly, with data discretization, we replace exact continuous numerical values with interval labels or higher-level concept hierarchies. So instead of storing exact ages for thousands of people, we just swap those numbers for broader concepts like youth, middle-aged, or adult. So we've washed, integrated, transformed, and reduced. And when you step back and look at this entire process, it becomes abundantly clear that data extraction, cleaning, and transformation actually comprises the vast majority of the work in building a data warehouse. Which leaves us with one final provocative question to chew on. If their real-world data is this dirty, and pre-processing is where the heavy lifting truly happens, are we focusing entirely too much on the flashy, complex algorithms and not nearly enough on the dirt? Thanks so much for joining me on this explainer, and I'll catch you on the next one.